All right, so this video is going to be on DeMoivre's theorem. I think I'm saying that right. But basically what DeMoivre's theorem is, we are taking a complex number and we are raising it to a power. Now that power could be like to the power of 6 or 8, or it can be a root, so 1/6 or 1/8. But the process to use this theorem is the same whether we are raising it to a power or a root, okay? So the first thing that you have to notice is that in order to use DeMoivre's theorem, we have to be in trig form, all right? So usually we start in rectangular form, and when we are in rectangular form, that is when we use Pascal's triangle. So for number 3 in a previous video, that's what we used. Now, the being raised to the power of 3 is low enough to where, okay, I can write out Pascal's triangle and get to the 4th row. But what if it's to the power of 8 or to the power of 10? This process can get very tedious and it's not efficient. So when those numbers or those values are that high, we are able to use DeMoivre's theorem and it's not as tedious of a process, okay? So how does this work? So it says find root 2 over 2 plus root 2 over 2i raised to the 6th power. Answer in form a plus bi. So in this case, we're starting in rectangular, and then we have to go back to rectangular. But the intermediate step is that we have to convert to trig form in order to use DeMoivre's theorem, okay? So sometimes you have to change forms twice, depending on what the question is asking you to do. So to convert to trig form, we've talked about this a couple times already. We will use the unit circle. Root 2 over 2 is a coordinate. It's a standard coordinate on our unit circle. It's going to be in quadrant 1, and that means our radius, because it's a standard coordinate on the unit circle, the radius is 1, and then our theta, that is going to be, let's do degrees. We will always specify whether we want degrees or radians, but your theta will be 45 degrees. All right, and if you obviously with the unit circle, the unit means 1, radius of 1. But if you're in like you're on an assessment and you're forgetting things, always remember that r, you can use the Pythagorean theorem and you'll end up with 1 again, okay? So in trig form, that means our complex number, we're raising it to the 6th power. That's going to be equal to 1 CIS 45. Now from here, to use DeMoivre's theorem, you apply the power to the radius, all right? So we're going to raise the radius to the 6th power, and then you're going to use that same power and multiply it with the angle. So we'll have 1 raised to the 6th CIS with an angle of 6 times 45 degrees. And then from here, just simplify and shorten it up. So we have 1 CIS, 6 times 45, that's going to give us 270 degrees. And that is within 0 to 360, so we don't need to adjust that in any way, shape, or form. Now, we are in trig form. We have the solution in trig form, but we need to convert back to rectangular form, a plus bi form. So to do this quickly, I'm going to go ahead and expand my CIS. So we'll have cosine 270 degrees plus I sine of 270 degrees. Now, if you recall from a previous video, to convert from trig to rectangular, all we do is evaluate. So we're looking at 270 degrees. That is going to be here at the bottom of the y-axis or the vertical axis. Cosine 270 will be 0. And then sine of 270 is -1. So we're just left with -I. And if you want, you can do 0 minus I, but these are equivalent. So either one will be accepted. And if you think about this, it makes sense. Our 45-degree angle is here. When we raise this to the 6th power, we end up down here. So I have 1 angle here, another theta here, 3 theta, 4 theta, 5 theta, 6 theta. So when I add those 6 of these angles together, I end up at 270. The radius does not change, so it's still going to be 1. So hence we get -I. This next one, it says find -2 plus I root 7 raised to the 5th. Use DeMoivre's theorem, leave answer in trig polar form. So now in this one, we still have to convert to trig form, but we don't have to convert back to rectangular because it says we can leave it in polar or trig form. For this one, we will go from 0 degrees to 360 degrees. So we'll be in degrees again. Now this one will require a calculator. So I'm going to go ahead and quickly pull up the calculator. I think I have it saved. Yep. Okay, get these adds out of the way again. Whoops. These used to not be here. I guess somebody may have bought it out or something. And let's split the view and get the notability up. All right, awesome. So I'm gonna go to mode and I'm gonna make sure that I am in degrees. When you reset your calculator, it automatically goes to radians. So with this one, you'll wanna convert it to degrees. All right, so we need to find our radius and our theta. We are in quadrant 2, so we go up back -2, up root 7. So to find the radius, we'll use Pythagorean theorem. So I end up with -2 squared plus square root of 7 squared. And when we do this, we get 4 plus 7, so we have root 11 as the radius. So even though we're using the calculator, please always leave these exact. Don't type in square root of 11 and use the approximated the 3 decimal approximation. If you can keep it exact, leave it exact. All right, we want to be as exact as possible, okay? Now for the theta, it is in quadrant 2. So our theta is here, which means since I'm using the calculator, I will use this beta, okay? So in quadrant 2, just to recall, in quadrant 2, to find theta, we do 180 minus beta is equal to theta. Now with this one, we'll have tangent beta is equal to the absolute value of opposite over adjacent. Our opposite is root 7, and then our adjacent is 2. So that means beta is equal to inverse tangent of root 7 over 2. And when we type this in the calculator, I'll do second tangent, square root of 7 over 2. We end up with 52.913 degrees. Now, when we apply this to the fact that we are in quadrant 2, I will do 180 minus beta. So make sure when you're putting this in the calculator, don't type 180 and then minus and then type in just to the 3 digits. You need to go up, copy it, and then evaluate it that way, okay? So to show this, I do 180 minus beta because that's my exact. My approximation is the 3 decimal. So now I get 127.086 degrees. So when I write this in trig form, I'm raising it to the 5th power, so z raised to the 5th. Our radius is root 11, and then I have CIS. Sorry, I need to raise that. So we're raising it to the 5th power. So because it's a square root, it's already raised to the 1/2 power. So we'll have 11 raised to the 5/2. But let me go ahead and write this. So I'll write it as root 11 CIS 127.806 degrees, and we're raising this to the 5th. There we go. That way we can see that we are applying it to the radius and to the theta. So I'll have 11 raised to the 5/2, and then CIS, we will multiply this angle with 5. And from here, we can just simplify. We don't have to convert back to rectangular, so I'm going to use the shortened CIS version. So I have 11 raised to the 5/2, CIS, and then I'm going to take this angle, multiply it by 5. And again, I copied it from the calculator. I'm not using the 3 decimal approximation. So I end up with 635.433. However, this is out of our domain restriction, so I'm going to subtract 360, and I get 275.433 degrees, and that will be our final answer. All right, so another way to use DeMoivre's theorem is when you're raising it to roots, okay? So rewriting the roots in exponential form, okay? We will still apply the same process. You will take this exponent, apply it to the r, and then you still multiply it with theta, but because you're multiplying theta with a fraction, we essentially end up dividing. However, I don't like saying dividing by the power because if you were to divide by 1 over n, that would change it to n times theta, which means you're not applying it correctly. So still think of multiplying, okay? Something else to remember is that when we have the square root of x, that's equal to x to the power of 1/2. If you have the 4th root of x, that's equal to x raised to the 1/4. Therefore, if we take the nth root of x, this is equal to x raised to the 1 over n, okay? So now what happens when we're raising it to a root instead of to a certain power? We end up slicing that complex number into even slices. All right, so this is the roots of a complex number. And again, we have to be in trig form for this. Okay, so same rule applies as if we were raising it to a power. If we are finding the third root, which means we are raising it to the power of 1/3, this means you will have 3 roots spaced 120 degrees apart. And we get the 120 because we are going to find the roots within 1 revolution, so 360 degrees or 2 pi. So we take 360 degrees and divide it by 3, which means the roots will be evenly spaced by 120 degrees. If we were to visualize this, we could end up with a solution here, and here. And if you notice, because these are evenly spaced, these points become the vertices of a 3-sided polygon, aka a triangle. And because they are evenly spaced, it will be an equilateral triangle. And this pattern follows for however many roots we have, because the roots, n has to be an integer. So we're not going to get like raised to the 1/2.5, right? If we take a 4th root, we will have 4 roots spaced. And if we think 360 divided by 4, we get 90 degrees apart. So 360 divided by 4. And if we were to think about this, this would create the vertices for a 4-sided polygon, which will be our square. And if we do one more, say that we raise it to the 5th root, this means we have 5 roots evenly spaced. We think 360 divided by 5, that will be 72 degrees apart. And that's because 360 divided by 5 is 72. We will end up with a pentagon. So I believe it's 1 solution in quadrant 1. We could have 2 in quadrant 2, 1 in quadrant 3. Oof, this is not so good. And this continues on up basically to any integer that we want, okay? So now what is this going to look like analytically? So the next part says find the 5th roots of 3 plus 4i using DeMoivre's theorem. And we will need a calculator for this one. Just looking at 3 and 4, I know that that's not going to be a standard coordinate on the unit circle, okay? So if we start with our conversion, we need our radius and we need our theta. So 3 plus 4i, we're going to be in quadrant 1. And if you notice, the base is 3. Height is 4, which means our radius will be 5. So we'll do 5. 3, 4, 5 triangle. Again, if you're like in an assessment and you're kind of sweating a little bit, use Pythagorean theorem and then you'll get 5 again. Now for our angle, we can use tangent theta. We can just use theta because we're in quadrant 1, because that's going to be the standard angle. And this is going to be equal to opposite over adjacent, which is 4/3. Which means theta is equal to inverse tangent of 4/3. And if we type this in the calculator, let's see, 4/3, we end up with 53.130 degrees. So that will be our theta. So that means if we are raising this, it says find the 5th roots. We are raising this to the power of 1/5. Because we are taking the 5th root of our complex number, okay? So I'm going to rewrite my complex number. We have a radius of 5, and then our angle is 53.130, and this is all raised to the 5th. Sorry, I'm running out of space, but we'll go down. All right, so that means I'm going to take the 5th root of 5. I'm still going to apply the power to the radius, and then I multiply it with the angle. So I have CIS, so we'll have 1/5 times 53.130 degrees. So again, even though we're using a fraction, it's the same process that we did when we rose this complex number to a power. We still just raise the radius to that power and then multiply the angle by that power. So I have the fifth root of 5 CIS. Now I'm going to copy it. I'm still using the exact value in the calculator. So times, it's the same as 0.2. So we'll do that. So I end up with 10.626 degrees. Now that is my first solution. All right. Now, since we are raising it to the fifth root, if I do 360 divided by 5, I end up with 72 degrees. That means all of these roots are separated, evenly spaced by 72 degrees. So if I went to find the next one, I'm going to add 72 to my first angle, which is 82.626. So I'm going to say that this is my first solution. My second solution is root 5, the fifth root of 5, CIS, 82.626 degrees. Our third solution, we'll have the fifth root of 5, CIS. I'll add 72 again, and we get 154.626 degrees. Z sub 4, we'll add 72 again. I get the fifth root of 5, CIS, 226 degrees, 0.626. Sorry, 226.626 degrees. Z to the fifth, Z sub 5, we get the fifth root of 5. There's a lot of 5s. CIS, I'll add 72 one more time, and I get 298.626 degrees. And those are my 5 solutions. So you should never go above 360. If you end up going above 360 degrees or 2 pi radians, then you messed up somewhere, because this is only going to be within that domain restriction, okay? The last topic is going to be roots of unity. So roots of unity means that we are dealing with a radius of 1 and we are starting at our standard angle of 0 degrees, okay? So roots of unity, what these do is they form the vertices of a regular polygon a regular n-sided polygon, because we're still dealing with integers, inscribed in the unit circle in the complex plane. So roots of unity, unit circle, they all mean 1, right? So roots of unity means z raised to the power of n is going to be equal to 1. So that means in the complex plane, we are starting here, okay? So the complex number that we are dealing with is going to be starting at 1. So we want the 10th roots of unity. Unity means 1, so we essentially want the 10th roots of 1, starting at 0 degrees, okay? So whenever you're dealing with roots of unity, your first solution will always be this. 1 CIS 0 degrees, because our home base will always be 0 degrees, and it will always have a radius of 1 because we are inscribing these n-sided polygons onto the unit circle in the complex plane, okay? And we will always start at 1. Now from here it says the 10th roots of unity. We want the first 5. 10th root, so we're going to do 360 divided by 10, so we get 36 degrees. So that means starting from 0, I will add 36 degrees, and we end up with 36 degrees. And then I continue on from here. So if I add 36 to 36, we get 72. Add 36 to 72, we end up with 108. And then add 36 to 108, we end up with 144. So in the complex plane, we have 0 degrees. Let's see, 36 will be like here, 72, 108, 144. And this would keep going until we had 10 solutions. So I think we end up with a decagon, is what that's called, a 10-sided polygon that would continue around, but we just had to find the first 5. So roots of unity, you always start here. In the complex plane, that is 1 plus 0i. And then you add however many degrees from there, depending on which roots of unity you are finding. That concludes this unit. Hope this is helpful.